Hello, everyone. How are you? I hope it's well. Oh, thank you for joining for us. Yes. Let me introduce the new speaker of our talk. It's Katerina. Katerina is a software test engineer who will share her knowledge and experience about the quality and our talk. Katerina, go ahead.
Hello, everyone. As I was already introduced, my name is Ekaterina Mitasova, and I'm excited to share some of my findings on measuring quality. So, today's presentation is how quality is measured. I've been working as a QA engineer for the past 5 years. I have experience with different projects, and on each project, there have been different approaches to quality measurement. So, today we'll review the definition of software quality, the balance between functionality, usability, performance, security, and maintainability, approaches, tools, and techniques to measuring quality, and alignment of quality with business and user expectations. So, today, on most projects, there are fast development cycles, and therefore, measuring quality is crucial to ensure early defect detection, maintaining stability, user satisfaction, compliance and security, optimizing development efforts, and reducing technical debt. As well, there are faster time releases. But what is actually quality? You can now see in your screen the definitions, the official definitions by ISO and IEE, but let me encompass them. So, software quality refers to the degree to which a software product meets the expectations of stakeholders and conforms to its functional and non-functional requirements. It encompasses such attributes as reliability, performance, usability, security, and maintainability. Together, these quality attributes determine how well the software fulfills its intended purpose and provides value to end users. So, you can see the definitions by ISO, International Organization for Standardization, and IEEE, Institute of Electrical and Electronics Engineers. So, these two definitions are about what I've just said. And as I've already mentioned, software is viewed as a combination of functional quality, non-functional, and customer satisfaction. So, functional quality shows how well the software meets its requirements and intended purpose without defects. Non-functional quality includes attributes such as scalability, usability, and security that enhance user experience and system reliability, and customer satisfaction relates to the degree to which the software fulfills end user needs with minimal errors or frustration. It's important to balance these quality attributes. And such quality attributes as functionality, usability, performance, security, and maintainability have competing priorities. So, let's now view each quality attribute and see how they can actually be competitive. The first one is functionality. The core purpose of software is its ability to perform tasks as it was designed, and the designs are specifications. And functionality is the foundation of software, but meeting functional requirements alone isn't sufficient. For example, a highly functional software application will fail if it's too slow due to performance issues or difficult to use due to usability issues or insecure. The second attribute is usability. It demonstrates the ease with which users can understand, navigate, and accomplish tasks in the software. Usability should be balanced with other quality attributes. For example, a highly usable application may require trade-offs with complex features. For instance, prioritizing simplicity could limit advanced functionality, and poor usability can overshadow great performance or functionality if users cannot easily interact with the system. The next quality attribute is performance. Performance shows how efficiently the software performs tasks under normal and stress conditions. For example, here we can measure response times, resource utilization, and scalability. Again, it is important to balance different aspects. Exceptional quality or usability can feel useless if the software is slow or crashes under load. And over-prioritizing performance may lead to feature restrictions or difficulty in maintaining usability and functionality. The next quality attribute is security. It is necessary for safeguarding the software and its data from unauthorized access, breaches, and vulnerabilities. So, some examples showing why balance is important. High security may add complexity. You know all these applications with multi-step authorizations, and they can reduce usability or just slow performance. And conversely, prioritizing speed and ease over security can expose the product to risks. And the last one we are reviewing, the last but not least, is maintainability. It can be described as the ability to fix, update, and enhance software efficiently while minimizing disruption. So, again, we need here balance because overly complex software which prioritizes functionality or performance can reduce maintainability, and it can make updates and debugging costly and time-consuming. On the other hand, hyper-focus on simple code for maintainability might sacrifice advanced functionality and scalability. The main conclusion for this part, with the review of quality attributes, is that they are interdependent and are often in conflict. Boosting security may negatively affect usability, enhancing usability may conflict with achieving complex functionality. Balancing these attributes requires collaboration between QA teams, developers, and stakeholders, and here are several priorities: context, criticality, and risk versus benefit. Context is defined by industry, product type, and user needs. For example, banking apps may prioritize security, while e-commerce apps may emphasize usability. Criticality. What is important to the user? For example, functionality and security might outweigh performance for a banking app. And risk versus benefit. We should address high-risk areas, for example, security vulnerabilities, when we optimize value-added features. So let's move to the next concrete example. You can see the slide about Toyota, and it's a real example that happened to Toyota. To ensure that we truly meet all the requirements, it will be useful to measure quality. And here, we understand that a failure to measure quality in real life can lead to a big failure. So, a famous example of this is Toyota's unintended acceleration recall in 2010, and it involved a potentially lethal defect in its onboard software systems. In 2009-2010, Toyota recalled over 8 million vehicles due to a dangerous defect. Cars accelerated unintentionally, causing accidents, injuries, and fatalities. This issue was traced to the electronic throttle control system, and poor quality measurement during software development led to insufficient testing of safety-critical features, lack of fail-safe mechanisms to prevent or mitigate errors, and to failure to account for edge cases and abnormal scenarios in the system's performance. This failure underscores the vital role of quality measurement in identifying software vulnerabilities before they cause damage. The lack of robust testing and safeguards resulted in lives cost. Poor quality can have life-threatening consequences. Financial and legal costs. Toyota paid $1.2 million in criminal penalties and billions more in settlements and recalls. And reputation damage. At that time, consumer trust in Toyota reliability declined significantly. So, key QA lessons here. The first one is rigorous testing. Quality measurement must include thorough testing in real-world and edge case scenarios. The second one is about fail-safe mechanisms. Redundancy and safeguards are critical for safety-critical systems. And system-wide QA, cross-functional reviews ensure software works reliably with hardware. The Toyota case illustrates that quality measurement isn't optional, it's essential. Robust QA processes prevent catastrophic failures, protect lives, and preserve trust in the product. And every QA team must prioritize quality measurement to ensure software delivers safety and reliability. But the definition of software quality has evolved over time. Now you can see in the slide traditional approaches to software quality. These changes from traditional to modern approaches happened because there have been advancements in technology, methodologies, collaboration models, and user expectations. So let's view a breakdown of traditional versus modern quality approaches, and let's see how they are different. So traditional approaches. They are rooted in waterfall development. They focus on detecting defects after software is developed, and QA and testing are often treated as a separate phase performed after coding is complete. QA roles are distinct from development, creating silos between developers and testers, and there is heavy reliance on manual testing, and there are predefined test plans. There are a lot of challenges of traditional approaches. Catching defects late in the cycle increases costs and delays. Siloed processes lead to communication gaps between QA, developers, and stakeholders. There is limited focus on end-user experience, usability, and agility. And there are struggles to adapt to changing requirements, and changing requirements are now common in dynamic business environments. Modern approaches to software quality are quite different. They are rooted in Agile, DevOps, and methodologies like CI/CD, which stands for Continuous Integration, Continuous Delivery. Quality is treated as a shared responsibility across the entire team. So everyone in the team is responsible: developers, testers, stakeholders, and so on. There is also a shift-left mindset that focuses on building quality into every stage. What it is, I'll describe later, but in a nutshell, a shift-left mindset is about testing as early as possible. And there is heavy reliance on automation tools, collaboration, and real-world validation methods. Modern approaches have a lot of advantages. Early detection of defects reduces time and cost of fixes. It also supports dynamic requirements by adapting to changes in Agile and DevOps environments. Also, modern approaches improve collaborations through shared ownership of quality, and they ensure high-quality delivery through focus on real-time testing, user feedback, and rapid iteration. Also, modern approaches encourage robust software design and architecture by embedding quality from the start. And now, a lot of modern tools support pipelines, CI/CD, automated code analysis, for example, Selenium, Jenkins, and SonarQube. So now you'll see in your screen the table comparing traditional versus modern approaches. And as we can see, traditional approaches were sufficient for static, longer lifecycle projects with well-determined requirements, but they lack the flexibility, collaboration, and speed demanded by modern software development. And modern approaches emphasize continuous quality, early testing, automation, and that all makes them ideal for today's fast-paced Agile and DevOps environments. They integrate QA into the development cycle, reducing risks, enabling faster feedback, and these modern approaches foster collaboration to deliver reliable and scalable software. And the methodologies of software, such as waterfall and Agile DevOps, go beyond just development process. They also determine how quality is measured, assured, and improved throughout a project. So, how project is measured in waterfall? In waterfall, there are sequential phases. Quality is measured at some specific stages, for example, after development in testing phases. And in Agile and DevOps methodologies, there is iterative, continuous quality measurement. So quality is measured constantly throughout short development cycles or sprints or in a CI/CD pipeline. So now let's discuss a couple notions that are widely used in modern approaches. One of them is shift-left testing. Shift-left testing refers to the practice of moving testing and quality-related activities as early as possible. That's why it's called left. It's early in the development life cycle. And the key features of it are early defect detection, because testing is performed during the requirements, design, and coding stages, and this reduces the cost and complexity of fixing defects. There is also integration of testing and development. Developers are actively involved in testing. They use techniques such as unit testing, code reviews, and static code analysis. There is a heavy use of automation. Automated tools are integrated into the development pipeline. And this allows such tasks as regression testing, performance testing, and security checks happen earlier. And there is a focus on requirements testing. It's also referred to as shift even further left. Quality engineers participate in requirements and design reviews to catch misunderstandings or ambiguities early. And there is iterative and frequent testing. Testing occurs in parallel with development, as in agile sprints, ensuring each incremental deliverable is thoroughly tested. So why shift-left testing matters? First of all, it's because of cost efficiency. Fixing defects earlier is significantly cheaper than addressing them in later stages of post-production. There are shorter feedback loops. Developers receive real-time feedback, and it enables faster resolution of issues. There is improved quality. With continuous testing, software is more reliable and meets end-user expectations from the outset. And there is reduced risk in production. Early performance and security testing mitigate production risks. Now, let's review an example in action. A developer commits code to a repository. After that, automatic static code analysis tools are triggered to reveal coding violations and security flaws. Then, unit tests are run automatically to verify code correctness. And this all improves immediate feedback and reduces the need for defect fixing during some later iteration, as it would happen in traditional approaches. The other notion commonly used in modern approaches is continuous quality improvement. Continuous quality improvement is a systematic, iterative approach to enhancing software quality by continuously analyzing, testing, and improving processes and products throughout the software lifecycle. It's characterized by ongoing iteration. Ongoing iteration means that quality is not a one-time goal, but a continuous effort across multiple releases and updates. Also, it's characterized by metrics-driven improvement. It means that quality of the product is evaluated against key metrics. For example, defect density, test coverage, user feedback, and in such a way we identify areas of improvement. Also, there is cross-functional collaborations. Developers, testers, operations, business stakeholders all work together to identify and resolve quality gaps. There is also learning from feedback. CQI relies heavily on continuous feedback loops, whether it's from user input, production monitoring, or retrospective reviews, as we have them in Agile. And there is focus on non-functional qualities. Continuous quality improvement emphasizes continual improvement of performance, security, usability, and ease of maintainability. Why it matters? First of all, it means easier adapting to change. CQI ensures that the software evolves with user needs, new business goals, and emerging technologies. There is also reduced technical debt. Regular quality checks and process improvements prevent the accumulation of unoptimized code. And there is enhanced user satisfaction. By integrating user feedback over time, CQI creates products that are more relevant and aligned with user expectations. Let's review some example in action. For example, in a DevOps pipeline, real-time production monitoring tools such as Dynatrace or New Relic identify some performance bottlenecks post-deployment. And insights are fed back into the development process so issues can be fixed in the next iteration or release. And as in agile practices, we have retrospective meetings. In retrospective meetings, we analyze some missed opportunities and set goals for future improvements for next sprints. As we've discussed, these notions are quite different. You can see now the table with these differences. But still, it doesn't mean these two approaches cannot work together. For example, how they can work together. Shift-left testing ensures quality from the start by embedding proactive testing into the early stages of development. And continuous quality improvement builds on this foundation. It monitors and refines quality practices throughout the lifecycle to adapt to evolving requirements, and also we learn some lessons by such review. For example, during development, a team integrates shift-left testing practices like static code analysis and unit tests. And after deployment, so here we use continuous quality improvement, the system monitors performance and gathers users' feedback, and it informs enhancements for the next iteration. So, shift-left testing focuses on preventing defects early in the development by embedding testing into earlier phases, while continuous quality improvement ensures quality is a continuous goal. So it uses feedback loops and iterative improvements across the software lifecycle. And together, these two approaches create a robust, proactive, and adaptive quality framework, which is perfectly suited for modern agile and DevOps environments. And measuring the quality of software is essential to ensure it meets some functional and non-functional requirements. It's also essential to deliver value to users, align with business goals, and approaches to software quality measurement primarily focus on quantifying attributes such as functionality, performance, reliability, usability, security, maintainability, and we can have some metrics and key performance indicators, KPIs. These approaches include manual evaluations, automated testing tools, and continuous monitoring throughout the software lifecycle. So let's move on. Approaches to measuring software quality. The first one is requirement-based testing. It validates whether functional and non-functional requirements, business needs, user expectations are met. And we can use traceability matrices to ensure test cases align with the requirements. For example, we check if features work as intended or specific performance benchmarks are achieved. The second one is process-based measurement. It's often also referred to as QA process evaluation. It measures the effectiveness of development and testing practices, for example, defect discovery rates and test coverage. It focuses on adhering to QA workflows, resolutions of defects, and ensuring test plans align with goals. For example, we compare the number of passed versus failed test cases during regression testing. User-centric testing, also referred to as validation. It assesses quality based on user experience and satisfaction. For example, we can collect feedbacks through surveys, usability testing, and monitor task success rates. Such an example can be tracking session duration and error rates during usability testing for some, let's say, e-commerce application. The fourth one is data-driven measurement. It uses data generated during testing phases and production monitoring to evaluate metrics. For example, we can measure defect density and response time. For example, in practice, we can analyze some logs and transaction records to measure system performance. Also, another approach is automated testing and monitoring. Tools such like Selenium, Gmeter, SonarQube, or Dynatrace can automate quality checks. For example, security scanning, performance testing, and code coverage. And continuous monitoring in production defects, anomalies, regressions, or service level agreement violations. And also we have such a notion as benchmarking. Benchmarking compares the software against some industry standards or competitor products to evaluate relative quality. For example, such a standard exists as the Open Worldwide Application Security Project. It's a non-profit foundation dedicated to improving software security, and they have certain guidelines that help us to compare our product, whether it's compliant to these guidelines. So now let's have a look at the key metrics to measure software quality. Each measurable attribute in software quality contributes to it corresponds to some specific metrics. So you can see in your slide these typical metrics. The first one is the functional quality metrics. It measures how well the system conforms to functional requirements. So here we can measure, for example, defect density. It's number of defects per unit of code. For example, we see how many defects we have per 1,000 lines of code. Also here we can measure defect leakage, percentage of defects discovered after release. It's often referred to as escape rate. And requirements coverage, percentage of all test cases covering all documented requirements. The second one is performance metrics. They measure how efficiently the software operates under various conditions. For example, they can measure time taken by the software to respond to user actions. For example, the user clicks a button, or we can query a database, and we measure how much time it took the system to respond to our inputs or requests. And lower response times improve user experience. For example, if a website takes 3 seconds to load, a user clicks to link, the response time is considered 3 seconds. And it's a good practice to keep response times under 2 or 3 seconds for web applications, and for real-time systems, it may be even in milliseconds. Another measurement is throughput. For example, we can measure number of transactions processed in a given time period. Throughput is applied to measure how much the system can handle. For example, how many requests per second on transactions per minute the system can handle. And the purpose of it is to evaluate the system's capacity and capability to process high volumes of data or user interactions without any degradation. For example, an e-commerce site can process 1,000 orders per minute during a Black Friday sale, and this metric is crucial for scalability. And it's a good practice to aim for throughput that surpasses expected peak user or transaction demands. Here we can also measure latency. It is delay between initiating and completing a request. And scalability is measuring performance during increased user load or resource demands. Also, we can have reliability metrics. They measure the consistency and dependability of the software. Here we measure mean time between failures. It's average time the software operates before experiencing a failure. Also, we can measure mean time to repair, average time taken to recover from some defect or failure, and availability uptime. It's percentage of time the system is operational and accessible. Usability metrics measure how easy it is for users to learn, navigate, and successfully interact with software. So we can practically measure task success rate, percentage of correctly completed tasks during usability testing. We can also measure time on task, average time users take to complete tasks, to see how difficult it is to navigate within the system. We can also measure error rate, percentage of errors made per user action, and user satisfaction score. It is collected via surveys about ease and satisfaction. And also we have security metrics. Security metrics measure how well the software is protected against unauthorized access or vulnerabilities. Vulnerabilities can be categorized by severity, critical, high, medium, low priority. And the total number of these identified vulnerabilities can be measured during security testing or auditing. And its purpose is to identify and track potential risks in the software and help to prioritize fixes based on the threats and their impact. The examples of such vulnerabilities are SQL injection, cross-site scripting, insecure authentication, buffer overflows, or exposure of sensitive data. And there are certain thresholds. Ideally, critical and high severity vulnerabilities should be zero before deployment. And medium severity vulnerabilities may require some fixes depending on the likelihood of exploitation, while some low severity issues may be resolved later over time. And we have some tools to help us with these tasks. These are vulnerability scanners like OWASP Zap, Nessus, Burp Suite, and Qualys. They all help automate vulnerability detection. And also, security compliance also measures how well the software complies with security standards, policies, and industry regulations. One of such examples, usually people in EPAM refer a lot to, and we in EPAM know it, is GDPR, protection of personal data for European citizens. Software security can be measured during static application security testing when we review code. It happens early in development. It can also be dynamic when the application is already run. Also, there is such a notion as penetration testing or pen testing, when security experts simulate attacks to discover some vulnerabilities in the software. There is also vulnerability scanning. It is about regular scans of the application and its dependencies. Here, by the way, here we can use Nessus or Qualys, these tools that I mentioned. And there are also security audits, comprehensive manual or automated reviews to ensure the quality the software quality complies with some organizational or legal security standard. Here we also have threat modeling to identify potential threats to the system, and continuous monitoring. Continuous monitoring is about regularly monitoring applications and infrastructure for real-time alerts. And maintainability metrics. They measure how easy it is to update, fix, and scale the software. Here we can have such a metric as code complexity. We use tools to track factors like cyclomatic complexity. It is logical complexity of code. We can measure test coverage, percentage of the code base tested, ensuring coverages of critical errors. Here we have also refactoring rate at which inefficient or outdated code is revoked and improved, and change failure rate, percentage of releases or updates that cause some defects or maybe even downtime. So we've just discussed metrics, but we also have KPIs. A critical difference between metrics and KPIs is their level of focus. KPIs have a high-level perspective. They represent key goals the business and technical staff should achieve. And conversely, metrics are considered lower-level indicators, and they just track activities or process data specific to some areas. So, the key performance indicated in software quality. The first one is defect escape rate, percentage of defects discovered after release. So, the lower rates we have, the better it is. It means there was better pre-release testing and QA in general. The second one is test effectiveness rate. It is a percentage of tests successfully identifying defects, and high effectiveness correlates with robust testing coverage. There is also deployment frequency of successful releases in a DevOps CI/CD environment. High frequency without regressions is ideal. A customer satisfaction score, it is user feedback scores indicating how satisfied the users are with the product experience. Application downtime, amount of times the application is unavailable, first time fix rate, percentage of defects fixed on the first attempt without causing any new defects. As well as we all know, there can be some fixed issue and it can cause new defects. And the last KPI is software scalability. It measures how well the software performs under increasing user load without degradation. So, why metrics and KPIs matter? They provide quantifiable insights into quality, into software performance in general, into its reliability and usability. And it enables teams to identify weaknesses and prioritize improvements. And they drive accountability and help teams align quality with business objectives. And surely they improve decision-making. Some tools and techniques we have in QA. First of all, we use automated testing tools, such as Selenium, for example. It's open source tool for web application testing. It supports multiple programming languages like Java and Python. In these languages, you can create test scripts. Also, Selenium allows testing across different browsers like Chrome, Firefox. It also allows testing in different platforms. And also we have some other tools, such as, for example, Cypress. Cypress is JavaScript-based end-to-end testing framework focused on modern web applications. And it's popular for real-time interactivity and seamless debugging. Also, it's known for fast execution environments for front-end and API testing. And we can use it together with React and Angular apps. And also, another popular app is JUnit. It's it's a unit testing framework. It's testing framework that helps developers write and run some repeatable tests. And also another technique is code quality analysis. Code quality tools analyze software quality to identify vulnerabilities, maintainability issues, and adherence to coding standards. Here we have SonarQube. SonarQube is a tool that measures code quality metrics such as bugs, code smells, security vulnerabilities, and maintainability. And it offers static code analysis for evaluating patterns in code bases across multiple languages. And it also helps determine in practice technical debt and ensure compliance with security standards. And another tool is Code Climate. Code Climate focuses on maintainability, test coverage, and identifying duplicate or poorly written code. It provides metrics aimed at reducing technical debt, and in practice, it's often used to monitor code quality trends across development teams. And we have also such technique as monitoring and observability. Monitoring tools track application performance, errors, and availability in real time to ensure software reliability in production. So we have such a tool as Datadog. Datadog offers monitoring and observability for infrastructure, application, logs, and user experience, and detects performance bottlenecks through infrastructure and real user monitoring. In practice, it's used often for observing server health, and it helps to identify delays in APIs and microservices. Also, another tool is New Relic. It provides application performance monitoring with insights into response times, error rates, and application downtime. And in practice, it's also often used to monitor resource utilization and slow-performing SQL queries. And interesting best practices are test automation strategies to ensure we use tests to achieve a faster feedback, and risk-based testing. Risk-based testing focuses on testing efforts on areas that pose the highest risk. And now let's discuss how we can also it's important to incorporate real user feedback, because real user feedback gives us understanding what users think. For example, we can use post-interaction surveys, Google Analytics, or Hotjar to track user behavior, to monitor support tickets, and frequently asked questions to identify some user pain points. And so now we are moving to this part, why it's important to align with business and user expectations. First of all, we know that quality is inseparable from business success. Poor quality has direct costs, and these costs increase the longer defects go unnoticed. For example, if a customer encounters a critical bug during a checkout, and for example, this is some e-commerce platform, then there is immediate revenue loss because the customer may not complete their purchase, and there is lost trust and reputation. Studies show that 88% of users are unlikely to return to a site after some frustrating experience. And cost of defects is more expensive the later it goes to deployment or post-release. For example, if we detect it early, it may be during code review and a developer can fix it. Then a QA may find it, and if a user finds it, it's quite bad. And it's important to bridge the gap between QA and business goals. We should talk to business in some clear terms, in business terms. We should translate metrics like defect density and test coverage into actionable insights. For example, we can highlight how fixing a usability bug improves conversion rates or enhances productivity for end users. And we can show how QA saves money, actually. For example, we can understand how the application works under high traffic events when there are a lot of users. So, in conclusion, I can say that early defect detection reduces cost, allows to communicate quality insights effectively to stakeholders, and prioritize user vote experience through UX testing and feedback loops. And it's important to remember that quality isn't just a technical achievement, it's our most powerful tool for growth, trust, and excellence. So it is worthwhile to use quality measurement in our projects. So thank you so much. And now I'm ready to answer some questions if you have any.
Thank you. Thank you, Katerina. Okay, they have some questions from Natalia. Natalia asked you about type end-to-end fast tool. If you have experience and if you have it.
End-to-end tool, sorry?
Okay. Natalia
Fast
asked you
tool.
about
I don't have my
type.
own experience with end-to-end fast tool, unfortunately. So I'm afraid I cannot mention something concrete. But it's a good question to investigate. Thank you so much for your question.
Okay, guys, we wait about second minutes, or maybe Kat explained it so well, but there are no questions left. Just wait. Katya, thank you very much. It will be it was very interesting and was useful information what shared with us. Very good talk.
Okay, thank you so
Thank
much.
you. Thank you. Stop. Yes, we have some guys questions about tools manage.
Yes, actually, it depends on what kind of KPIs and metrics you want to measure. For example, a KPI may be, for example, to measure escape rate, and it depends actually. We can measure escape rate, test effectiveness rate, deployment frequency, how well the users are satisfied. So it depends. For example, if you want to investigate customer satisfaction score, you can use surveys. These surveys that ask users some questions, how satisfied they are. Also, it's what we often see with mobile applications when they ask us to rate the application. But it's a totally different picture. For example, if you want to measure a KPI, how long the application is downtime, then we should refer to some tools that performance testers use. Or, for example, if you want to measure, for example, how well the application performs under heavy user load. Or, for example, manual testers can measure defect escape rate. We can even use Jira for it. For example, we can, in my project, we put a certain label when we find some defect in production, and we can see how many in this sprint we have not just defects, but defects discovered after release. So it varies on what you want to measure, because KPIs are for different metrics.
Okay, Katya. And Anton? Anton claims what E2E frameworks are all quite slow. What do you think about it?
It's a good question, but unfortunately, I'm a manual tester myself, and actually, in my project, we haven't encountered such a problem that we should make them faster. At least we haven't discussed it inside the team, and so I'm afraid, as a manual tester, I cannot figure out a way to make these frameworks any faster. So I'm afraid I can't know the way to make faster. Yes, computing power, sure, it matters. Yes.
Okay. Okay, guys, we don't have more questions, and I think thank you for joining. Thank you for joining. And if you need the presentation, you can contact with me on with our speakers if you need it. And have a nice day or weeks, and hope we see you next time. Bye bye, guys. Thank you, Katya. Bye
Thank you. Bye.
bye.